The concept of black holes. Black holes are some of the most mysterious and fascinating objects in the universe. They are regions of spacetime where gravity is so intense that nothing, not even light, can escape from them. The concept of a black hole arises from Einstein's theory of general relativity, which describes how mass and energy warp the fabric of spacetime. When an object becomes sufficiently dense, it can create a gravitational field so strong that it forms a black hole. The boundary around a black hole is called the event horizon. Once something crosses this boundary, it is irreversibly pulled towards the singularity at the center of the black hole. The singularity is a point of infinite density where the laws of physics as we currently understand them break down. Everything we know about black holes suggests they are the ultimate cosmic trap, with no escape once you're inside. Formation of black holes. Black holes are thought to form in several ways, depending on their size and type. The most well-known process is the collapse of a massive star at the end of its life cycle. When a star with a mass greater than about 20 times that of the Sun exhausts its nuclear fuel, it can no longer support itself against the pull of gravity. The core of the star collapses under its own weight, potentially forming a black hole. The outer layers of the star may explode outward in a supernova, one of the most powerful events in the universe. There are also smaller black holes, known as stellar mass black holes, which have masses ranging from a few to tens of solar masses. These are the remnants of stars that were not massive enough to become supernovae. Intermediate mass black holes, with masses between 100 and 100,000 times that of the Sun, are thought to form through the merging of smaller black holes or through the direct collapse of massive gas clouds in the early universe. The largest black holes, known as supermassive black holes, are found at the centers of most galaxies, including our Milky Way. These giants can have masses ranging from millions to billions of times that of the Sun. The exact process of their formation is still not fully understood, but they may have formed from the collapse of massive gas clouds early in the universe's history, growing over time by accreting mass from their surroundings and merging with other black holes. The event horizon and singularity. The event horizon is one of the most critical features of a black hole. It is the point of no return, beyond which nothing can escape the black hole's gravitational pull. The event horizon is not a physical surface, but rather a theoretical boundary. The size of the event horizon depends on the mass of the black hole. For a stellar mass black hole, the event horizon might be only a few kilometers across, while for a supermassive black hole it could span millions of kilometers. The singularity lies at the very heart of the black hole. It is a point where the curvature of spacetime becomes infinite, and the known laws of physics cease to function. The concept of a singularity is deeply tied to general relativity, but it also presents a significant challenge to our understanding of physics. At the singularity, densities become infinite, and the gravitational pull becomes infinitely strong. In practice, the singularity is hidden from view by the event horizon, meaning that it cannot be directly observed. What happens inside the event horizon is still a matter of intense speculation and theoretical research. Some theories suggest that the singularity may not be a point at all but could represent a bridge to another part of the universe or even to another universe entirely, a concept known as a wormhole. The growth of black holes. Black holes grow by accreting mass from their surroundings. This can happen in several ways. In binary star systems, where two stars orbit each other, one of the stars might end its life and become a black hole. The black hole can then begin to pull matter from its companion star, a process known as accretion. The matter forms a disk around the black hole, called an accretion disk, as it spirals inward and heats up due to friction. This heating can cause the disk to emit intense radiation, often in the form of X-rays, making the black hole visible to telescopes. Another way black holes grow is by merging with other black holes. When two black holes orbit each other, they gradually lose energy by emitting gravitational waves, ripples in the fabric of spacetime. As they lose energy, the black holes spiral closer together until they eventually merge into a single, larger black hole. The detection of gravitational waves by observatories like LIGO, Laser Interferometer Gravitational Wave Observatory, and Virgo has provided direct evidence of such mergers. Supermassive black holes at the centers of galaxies grow by accreting large amounts of gas, dust, and even entire stars. These black holes can become active galactic nuclei, where the infall of material creates extremely bright and energetic regions at the galaxy's center, often outshining the entire galaxy. Quasars, which are among the brightest objects in the universe, are powered by supermassive black holes accreting matter at an incredible rate. Hawking radiation and black hole evaporation. One of the most intriguing theoretical predictions about black holes comes from Stephen Hawking, who proposed in 1974 that black holes could emit radiation. This phenomenon, now known as Hawking radiation, arises from quantum effects near the event horizon. According to quantum theory, pairs of virtual particles are constantly being created and annihilated in empty space. If a pair of particles forms near the event horizon, one particle could fall into the black hole while the other escapes. The escaping particle becomes real, and from the perspective of an outside observer, it appears as if the black hole is emitting radiation. Hawking radiation leads to the gradual loss of mass from the black hole. Over incredibly long timescales, this process could cause the black hole to lose enough mass that it eventually evaporates completely. For stellar mass black holes, this process would take far longer than the current age of the universe, but for small black holes, it could happen much more quickly. Hawking's prediction was a major step forward in understanding the relationship between quantum mechanics and general relativity, although Hawking radiation has yet to be observed directly. Black holes and the information paradox. One of the most significant unresolved questions in physics is the black hole information paradox. According to quantum mechanics, information about the physical state of a system cannot be lost. However, if something falls into a black hole, it appears that all information about that object is lost to the outside universe when the black hole evaporates via Hawking radiation. This apparent loss of information conflicts with the principles of quantum mechanics, creating a paradox. Many theories have been proposed to resolve the paradox, including the idea that information might be encoded in the event horizon or in the Hawking radiation itself. Another possibility is that information is not lost but rather becomes inaccessible, trapped in some form at the singularity. The resolution of this paradox could have profound implications for our understanding of the nature of reality and the fundamental laws of physics. Black holes in popular culture and science fiction. Black holes have captured the imagination of both scientists and the public. They are a staple of science fiction, where they often serve as portals to other dimensions or as cosmic weapons. In reality, black holes are not the destructive forces often depicted in popular culture, but rather are fascinating objects that help us understand the extreme conditions of the universe. Movies like Interstellar have popularized the idea of black holes and introduced concepts like time dilation and gravitational lensing to a wider audience. In Interstellar, the black hole known as Gargantua plays a central role in the plot, and the depiction of the black hole was based on real scientific principles. The movie's visual effects team worked closely with physicist Kip Thorne to create one of the most accurate representations of a black hole ever seen on screen. Observing black holes. Because black holes do not emit light, they cannot be observed directly. However, their presence can be inferred by observing the effects they have on their surroundings. For instance, astronomers can detect the X-rays emitted by the hot gas in the accretion disk around a black hole. They can also observe the motion of stars and gas clouds that are influenced by the gravitational pull of a black hole. One of the most groundbreaking achievements in recent years was the first direct image of a black hole's event horizon, captured by the Event Horizon Telescope (EHT) in 2019. This image shows the supermassive black hole at the center of the galaxy M87, located about 55 million light-years from Earth. The image revealed a bright ring of light surrounding a dark shadow, which corresponds to the event horizon. This historic image provided strong evidence for the existence of black holes and confirmed predictions made by general relativity about the appearance of black holes.